In episode 78, titled ML Core Concepts, Learning, Loss, and What Optimization Really Means, the goal is to understand learning as minimizing loss, not magic prediction, because many exam errors come from treating machine learning as a mysterious intelligence rather than as a structured procedure with clear objectives. The exam cares because when you understand what learning really is, you can reason about why models fail, why metrics change, and what fixes are sensible, instead of guessing based on buzzwords. In real systems, the most important skill is not naming algorithms. It is knowing what the algorithm is trying to do and how that connects to business outcomes and operational risk. Learning is an engineering process. You define what wrong means, you search for parameters that reduce wrongness on known data, and you validate whether the reduced wrongness actually generalizes. Once you see it this way, you stop expecting models to be clever, and you start expecting them to be consistent with the objective you set. That mindset is what allows you to design, debug, and communicate models responsibly. Before we continue, a quick note. This audio course is a companion to the Data X books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series.
Loss is the penalty a model pays for wrong predictions on training data, and it is the mathematical definition of what the model is trying to avoid.
If the model predicts a value and the true value is different, the loss quantifies how bad that difference is, and different loss functions define different notions of bad. Loss is not the same as accuracy, because loss is often continuous and sensitive to magnitude, while accuracy is a discrete count of correct versus incorrect.
Loss is also not the same as a business metric, because loss is typically chosen for learnability and differentiability, while business metrics reflect operational outcomes and costs.
The exam expects you to recognize that the loss function is the objective during training, and the model will become good at minimizing that objective, even if that objective is not what you actually care about.
This is why loss selection is so important. It shapes what the model learns to prioritize. When you define loss clearly, you understand that learning is not vague improvement. It is targeted reduction of a chosen penalty.
Optimization is the process of searching parameter values that reduce loss, meaning it is a methodical attempt to find a better configuration of the model's internal settings. Parameters are the adjustable values the model uses to turn inputs into outputs, and optimization changes those values based on how well the model is doing according to the loss. The key idea is that optimization is not a guarantee of finding the best possible model. It is a search guided by the loss landscape and the algorithm's update rule. In practice, optimization can get stuck, converge to a good enough solution, or overfit, depending on how expressive the model is and how the data behaves. The exam often frames optimization as training and expects you to know that training is not the same as proving truth. It is minimizing a penalty on known examples. When you explain optimization correctly, you describe it as purposeful searching rather than as the model figuring it out in a human sense. This reduces confusion and makes debugging more grounded. Loss choice must connect to business cost because errors are not equal, and the exam frequently tests whether you can translate that reality into an appropriate objective. In some systems, large errors are far more costly than small ones, such as under-forecasting demand for critical inventory, and the loss should penalize large deviations strongly. In other systems, false positives are costly, such as blocking legitimate customers, and the learning objective and thresholding should reflect that cost. In yet other systems, false negatives are catastrophic, such as missing critical incidents, and the objective should push toward capturing true cases, even if it increases false alarms. The exam expects you to reason that if the business cost is asymmetric, your training objective, metric selection, and decision thresholds must reflect asymmetry rather than assuming all mistakes are equally bad. You do not always encode business cost directly into the loss, but you should at least choose a loss and evaluation strategy that align with the cost structure. When you connect loss to cost, you are aligning learning with outcomes rather than with convenience. Training is the phase where the model fits patterns to minimize loss on the training set, while testing is the phase where you check whether those fitted patterns generalize to new data. This separation is central because a model can always become good at the training set if it has enough flexibility, but the goal is performance on unseen cases. The exam cares because confusing training success with real success is one of the most common mistakes, and it leads to models that look brilliant in development and fail in production. Generalization depends on whether the patterns learned reflect stable structure or noise, which is why validation design and leakage prevention matter. Training also depends on the representativeness of the training data, because a model can only learn the world it sees, and drift changes what unseen looks like. When you keep training and testing distinct, you treat performance numbers as evidence conditioned on evaluation hygiene, not as universal truth. That is the disciplined perspective the exam expects.
Underfitting happens when the model is too simple to capture real structure, so it cannot reduce loss effectively even on training data, and it produces systematic errors that look like missed patterns.
This can occur when a linear model is applied to a heavily nonlinear relationship, or when features do not represent the mechanisms that drive the target, leaving the model without usable signal. Underfitting often shows up as both training and validation performance being poor and similar, because the model fails everywhere rather than only on new data.
The exam expects you to recognize underfitting as a capacity or representation problem, not as a tuning problem that can be solved by minor hyperparameter tweaks.
The remedy is often to add meaningful features, use transformations, allow nonlinear structure, or choose a more expressive model family.
Underfitting is also a cue to revisit target definition, because if the target is noisy or misaligned, it can make any model appear to underfit by obscuring signal.
When you diagnose underfitting correctly, you choose remedies that increase learnable structure rather than just increasing training time. Overfitting happens when the model memorizes noise and quirks in training data, reducing training loss while failing to improve or even harming validation performance. This is common when the model is highly flexible relative to the amount of data, or when features include leakage-like proxies that do not generalize, or when you tune repeatedly and implicitly optimize to a particular validation set. Overfitting often appears as a widening gap between training and validation performance, with training metrics improving while validation stalls or degrades. The exam cares because overfitting is the classic reason a model fails in the real world, and the correct fix is not to celebrate a training score, but to reduce degrees of freedom or increase evidence. Remedies include regularization, simpler models, more data, better features that represent true mechanisms, and stronger validation design. Overfitting is also a reminder that optimization will always reduce training loss if allowed, but that reduction is not the goal. Generalization is the goal. When you diagnose overfitting, you stop chasing lower training loss and start demanding stable validation improvement. Choosing a loss type by problem is a practical drill because regression, classification, and ranking tasks require different ways of measuring error. Regression loss measures the size of numeric prediction errors, often with different sensitivity to large deviations depending on the cost structure. Classification loss measures how well the model separates classes and assigns probabilities, and it supports threshold-based decisions while reflecting the cost of different misclassifications. Ranking loss focuses on ordering, meaning it penalizes putting relevant items below irrelevant ones, which matches prioritization workflows where the top of the list matters most. The exam expects you to match loss to the decision style, because training a ranking system with a pure classification loss can optimize the wrong behavior if the downstream action is top K triage. Loss choice should also consider learnability, because some losses are easier to optimize and produce more stable training than others, especially in noisy settings. When you can choose loss by problem type, you demonstrate that you understand learning objectives rather than only model families. Gradients are the signals that guide updates toward lower loss each step, and understanding this concept helps explain why training is iterative and why scaling and conditioning matter. A gradient tells you how the loss changes when a parameter changes, so it provides a direction in parameter space that should reduce the loss if you move a small amount in that direction. Optimization algorithms use gradients to take repeated small steps, adjusting parameters gradually rather than jumping randomly, which is why training often involves many iterations. Gradient behavior is also why poorly scaled features can slow training or cause unstable updates, because scale affects how large gradients become and how sensitive the loss is to changes. The exam does not require calculus, but it does expect you to understand that training is guided by feedback from error, not by random guessing. This also explains why learning rates and stopping rules matter. They control how steps are taken and when to stop taking them. When you describe gradients correctly, you demystify training into a feedback-driven improvement process. A common trap is focusing on one training metric while ignoring validation, because training numbers can always be improved by optimization, even when generalization is getting worse. The exam expects you to monitor validation performance, because validation is where you detect overfitting, leakage, and brittle improvements that do not translate. If training loss keeps dropping, but validation loss stops improving, that is a signal to stop training, adjust regularization, simplify the model, or revisit features, rather than to keep optimizing. Validation should be treated as the decision criterion for model selection and early stopping, while training metrics are diagnostics about whether the optimizer is functioning and whether the model is learning anything at all. This discipline also protects you from tuning toward a single metric that does not reflect business outcomes, because you can watch guardrail metrics and segment performance as part of validation. When you keep validation in focus, you align optimization with generalization, which is the real purpose of learning. Regularization adds penalties that discourage overcomplex models, effectively modifying the loss to prefer simpler explanations unless the data strongly supports complexity. The intuition is that complexity increases the chance of fitting noise, so penalizing complexity reduces variance and improves generalization. Regularization can take many forms, but the exam usually tests the concept you intentionally trade some training fit for improved stability on unseen data. This is also why regularization is closely tied to multicollinearity and high dimensionality, because redundancy and many weak features create many ways to fit training noise. Regularization does not create new signal, but it helps the model use the signal that exists more conservatively and consistently. The exam expects you to recognize regularization as a generalization tool, not as a performance gimmick, and to apply it when training outpaces validation. When you understand regularization, you see it as part of the objective design rather than as an afterthought. Optimization should be communicated as iterative improvement with stopping rules, because training is not a search you run forever. It is a controlled process that must stop when further improvement is unlikely or when overfitting begins. Stopping rules can be based on validation performance, such as stopping when validation loss stops improving, because that aligns training to generalization rather than to training fit. Stopping rules also matter for cost, because training consumes resources, and endless optimization can waste budget without delivering real outcome improvement. The exam expects you to communicate this as a disciplined loop. You choose a loss, you optimize, you validate, and you stop when evidence says further optimization is not beneficial. This framing also helps stakeholders understand that training is not a guarantee of progress, but a process that must be monitored and governed. When you present optimization as iterative, you reduce the myth of a single best training run and emphasize evidence-based model selection. A helpful anchor memory is choose loss, optimize carefully, validate honestly. Choose loss means define what error means in a way that aligns to the problem and, where possible, the business cost of mistakes. Optimize carefully means use disciplined training procedures, appropriate pre-processing, and regularization to prevent the optimizer from exploiting noise and quirks. Validate honestly means use proper splits, avoid leakage, and select models based on held-out evidence rather than training performance. The exam rewards this anchor because it captures the actual learning workflow: objective definition, controlled optimization, and honest evaluation. It also prevents the common error of treating optimization as the goal when validation is the true judge. When you follow the anchor, your models become better for the right reasons. To conclude episode 78, state the learning loop in plain terms. Predict, score loss, update, repeat. You start with initial parameters, use them to predict outcomes for training examples. Compare predictions to true values to compute loss, then update parameters in the direction that reduces that loss, often guided by gradients. You repeat this process across many iterations until validation evidence suggests you have reached a good balance between fitting training patterns and generalizing to new data. You then lock the model and evaluate it on an untouched test set to estimate real-world performance under the chosen design. That loop is what learning really means, not magic, but a disciplined procedure for reducing a defined penalty while continuously checking that the improvement is real, stable, and aligned to the outcome you actually care about. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.